In this tutorial, we are going to find out the procedure using Smith chart to calculate the input impedance of the transmission line. Now the input impedance equation for the transmission line is given to you over here. It is Zn is equal to Z0 into bracket Z0 plus JZn tan butyl in the numerator and Zl upon JZ0 tan butyl in the denominator. Beta is your propagation constant, which is equal to 2 pi by lambda g. Lambda g is the wavelength in the transmission line, also referred to as a guided wavelength. Okay, so using this equation, when the parameters are given to you, like all the impedances ZL, Z0, the length of the transmission line, the frequency of operation and the dielectric material for the transmission line, when all these parameters are given to you, you can find out the value of Zin. Okay, that is numerical procedure. We will understand today the procedure to find out the input impedance using Smith chart, and you can actually compare how much faster and accurate the procedure is. Okay, so various parameters are given to you. ZL, that is the load impedance, is given, characteristic impedance is given. Then you need to find out the normalized value of the impedance, that is obtained by dividing ZL by Z0. Then epsilon r, that is a dielectric material for the transmission line, is given, which is polyteflon, PTFE, what is called it as, or it is also referred to as a Teflon. And then length of the transmission line is given and the frequency of operation is mentioned. So the first part, what you are going to do is to calculate the value of L by lambda g. Now what is beta here? Beta is basically 2 pi by lambda g. Okay, so multiply that by L. So what matters, on parameter which the tan factor depends is the L by lambda g value. And L by lambda g value, it is also referred to as the electrical length of the transmission line. Because the scenario or the problem is something like this. This is the length of the transmission line which is given to you, and then you have a load which is connected. This is the length, and at this point you are finding out the input impedance. So what you are supposed to do, you are going to travel from input to the output side towards the generator. So how much distance you are going to travel? Remember, in Smith chart, we never specify the absolute values because it is a generic tool applied for all the frequencies, and always the dimensions, the parameters in the Smith chart are either normalized or they are expressed in terms of wavelength. Remember, they are expressed in terms of wavelength, so we should be clear with either the normalized values when it goes to the impedances, or we should be clear with what is the value of the length of the Smith chart transmission line in terms of operating wavelength. Because as we know, this is the open circuit point, short circuit point on the Z Smith chart. This is the open circuit point. So when you go from open to short or vice versa, you travel a distance of quarter wavelength. And when you complete one rotation in the Smith chart, you do a half wavelength travel. Okay, that is 0.5 lambda. So there is no specific value. The length of the transmission line is mentioned like 10 centimeter, 20 centimeter, like this. Everything is wavelength specific. Hence, we need to calculate what is L by lambda g value. We need to calculate what is L by lambda g value. So, for the first step in attempting this problem is calculate L by lambda g. So, substitute this parameter. Lambda g is basically C upon F under root epsilon r. So, substitute this parameter, you will get L by lambda g as 1.932. Okay, as 1.932. Now this 1.932, actually I can split it in more appropriate way. Okay, I'll explain you the reason why I am splitting it like this. So I can write 1.932 as 1.5 plus 0.25 plus 0.182. So all these add up gives me 1.932 value. I'll explain you the reason why I am splitting it this way. And this step is something very important while attempting this transmission line problem. Okay, so now let's first locate the impedance point on the Smith chart. Let's first locate the impedance point on the Smith chart. What is the point? 0.6 minus 0.4j. So that is the point what we are going to locate. So 0.6 is somewhere here, and remember it is minus 4j, 0.4j. So it is going to come down in the capacitive region. So point 4 is somewhere here, and so point 6 is here. The intersection of these two curves gives me the point. So this is my input, this is my load impedance. This is my load impedance. So point is located. Next step is to calculate or to travel this much distance on the transmission line. Okay, L by lambda G distance have to be traveled on the transmission line so that we arrive at the input location. So that we arrive at the input location. For that, the first step which involves is first draw the constant gamma circle. Why constant gamma circle? Because transmission line is lossless. Okay, it is not a lossy transmission line what we are dealing with. It is a lossless transmission line. So the value of reflection coefficient on the length of the transmission line remains same. It does not change as you move from output to input. So we are going to draw a constant gamma circle, what we call it as, and the procedure for that is take this radial distance from the center and draw a circle. Take this radial distance from the center and draw the circle. That is the first step. Second step what we involve, we need to initiate or we need to initialize the starting point. Okay, this starting point we need to initialize. Okay, for that what you do, you extend this straight line what is drawn towards the perimeter of the Smith chart. You extend this straight line towards the perimeter of the Smith chart. Now what we are going to do further using this? Remember, we need to decide how much distance. So distance we have calculated 1.932 is the distance in terms of lambda we are going to travel. So what is the reference? This is the reference point. So how you are going to move? Are you going to move in the transmission line in the clockwise direction or anti-clockwise direction? That you need to decide. For deciding that, just refer to what is written over here. Here it is written wavelength towards generator, wavelength towards load. Which means when you move along the Smith chart in the clockwise direction or when you move along this locus in the clockwise direction, you go towards the generator or the source. Whereas when you move along the anti-clockwise direction, that is in the reverse direction, you move towards the load. And now we are supposed to move towards the generator, hence we need to move on the locus in the clockwise direction. So how much to move now? For that, first initialize the starting point. First initialize the starting point. For that what you are going to do, you are going to read what is written on the outer scale over here. You are going to read what is written on the outer scale over here, that is the distance, the reference point. And you are going to refer to the scale for wavelength towards the generator. Now here, if you see the wavelength towards generator, it is written on the outer circle or on the outer perimeter of this circle, and wavelength towards load, it is written on the inner side. So what is being written over here, it is wavelength towards load, and what is being written over here, it is wavelength towards the generator. Okay. So addition of both will always be equal to 0.5. Addition of those will always be equal to 0.5. Why? Because one rotation on the Smith chart is 0.5 wavelength. Okay, so for that, so I need to initialize the starting point. So just read wavelength towards generator, that is the outer scale. Over here it is written 0.42. Okay, I am a little bit approximate over here because I am not drawing everything to the scale, but while doing a problem you can actually be to the precise to the scale and indicate the starting point. Okay, so this is the starting point which is there, and now after deciding upon the starting point, now you move 1.932 distance. Now you move 1.932 distance. For that, what you have to do is you need to split up this in the manner which I have shown. Remember, if I rotate, if I just move on this locus and come back over here, it accounts for 0.5 wavelengths. Okay, it accounts for 0.5 wavelength. So how much I have to travel? I have purposely splitted that into 1.5 plus 0.25 plus point remaining what is 0.182. So 1.5 travel, I will arrive at the same location. 1.5 travel, I will arrive at the same location. So when I am doing 3 rotations while doing a 1.5 travel, so I am arriving at a same location. 0.5 plus 0.5 plus 0.5 giving me 1.5. So I am arriving at the same location. So this much travel this much travel, I am arriving at the same location. So I need not move my point anywhere. Next, so I have already traveled 1.5. Next, how much it is? 0.25 plus 0.182. 0.25 travel accounts for the diametrically opposite point because you are doing a semicircle travel. 0.25 accounts for the diametrically opposite point, that is a semicircle travel. So what you do now, you extend this straight line and draw a straight line so that it is a diametrically opposite point is selected on the constant gamma circle. A diametrically opposite point. So when I am going to move from here to here, I am traveling a distance of 0.25. So again 0.25 is removed. 0.25 distance I have traveled. So this is also removed. So now just read what is written over here for wavelength towards generator. So it is around 0.166. It is around 0.166. Extend that line towards the upper line and then you read that value. It is 0.166. Okay, so that is the point you have arrived at after traveling 1.5 plus 0.25. After traveling 1.5 plus 0.25, this is the point you have arrived at. Now the remaining part. How much it is? 0.182. So just add 0.182 to this. So it is 0.348 is the final distance at which you are going to arrive at. Okay, so you need to locate a point on this outer circle where 0.348 is written. 0.348. So it is basically somewhere here. This is the point. 0.348. So you have done 3 rotations to cover L by lambda g is equal to 1.5. Then you have traveled diametrically opposite to additionally travel a distance of quarter wavelength, and then to this value you have added 0.182 as the additional length travel, so which accounts for 1.932 L by lambda g travel on the transmission line, so that you arrive from the load to the source, that is while calculating the Z-in value. So you have identified this point, 0.348. Next step is just draw a straight line which joins the center to this point. Draw a straight line which joins the center to this point. Okay. So after that, the point at which it intersect, the constant gamma circle is basically your Z-in. So how to read that? You apply the reverse procedure. Just see which R it coincides with. So it is approximately 1, and then just see which X it coincides with. Okay, so it is around 0.85. So the answer is 1 minus j 0.85 is the value of the input impedance of the transmission line. Of course, the normalized one, you multiply that with 50 ohm or rather Z0, you get the denormalized value. So this is how you are going to arrive at the input impedance of the transmission line using Smith chart. And if you really compare with respect to the calculation, the numerical equation what we have, it matches very closely with the value obtained using Smith chart. So and the procedure is also very fast. The only catch over here is your identification of L by lambda g value and appropriate splitting of this distance, so that you travel a complete circle or you travel a semicircle and then accordingly travel another distance which is remaining from that particular quarter wavelength or half wavelength travel, so that you arrive at the required input impedance location. So this is how you are going to solve it. Again, as I told you, critical part lies over in estimating the value of transmission line in terms of wavelength. If you are very clear in that, if that calculation is precise, your value will match to the perfect extent with the numerical calculations. So this is how we calculate the input impedance equation, input impedance of the transmission line using Smith chart. Now in the next lecture, we will start with the stub matching. Thank you.